Okay, today we're going to do a little bit on what a satellite is and do some calculations to figure out how we can figure out how long it takes a satellite or how fast it's going or how high it is above the Earth and so on. So first off, a satellite definition is any object that orbits some other object. So for example, a man-made satellite like our TV satellites, they orbit the Earth. But the moon also orbits the Earth, so we would call it a natural satellite. And the Earth would actually be a satellite of the sun. So a satellite really is anything that's orbiting some other body. And the origin of satellites actually goes back to Newton's time once again. So Newton had an idea where if we had the Earth, if he pictured the Earth as some sort of object, and he thought if we could launch a cannon, back in his days he thought of, okay, what's the fast thing I could move, and it would be like a cannonball. So he thought if he somehow had a cannon on the top of a mountain, and if he shot it fast enough so this cannon would get launched horizontally, he knew that gravity was going to pull that cannonball down to the Earth. So typically what would happen is the cannon would just follow a projectile kind of path and fall to the Earth. So his theory was, what would happen if we got this cannonball fast enough so that it actually, as it fell to the Earth, it actually matched the curvature of the Earth. So his theory was, is it possible that we could actually shoot the cannonball so that it would not ever fall to the Earth? It would just follow the same curvature of the Earth and would actually come right back to where it started. So his theory was, if we could get that cannonball going fast enough, it would actually escape the gravity of the Earth and it would orbit it around what we would now call as a satellite. So his theory was impossible to prove. He couldn't do it in his time. They couldn't get a cannonball to go fast enough. But what he actually did was, based on the Earth's gravity, he calculated that he would have to shoot this thing at 8 kilometers per second. So that doesn't sound too bad, but remember that's actually 8,000 meters per second. And if we convert that to kilometers per hour, it's actually almost 30,000 kilometers per hour. Okay, so what that means is an object on the surface of the Earth or on the top of a mountain or whatever, because technically it would hit some sort of things in the way, but anything near the surface of the Earth would actually have to travel at 28,800 kilometers per hour to be able to stay in orbit. Anything less than that, it would crash to the Earth. Anything bigger than that, it would actually leave the Earth. So in terms of space shuttles and things like that, that's basically sort of a target number. So for them to leave the orbit of the Earth, they would actually have to travel at like 30,000 kilometers per hour or something like that. In reality, we don't do that because we actually launch the rockets straight up, and the higher they get, the less the gravity is, then they don't need to be going quite so fast to be able to leave the orbit of the Earth. But gives you just sort of a general basic idea of what Newton thought of as being a satellite. So what that means is then if we have our Earth in a location, we can have a satellite orbiting at any different height or altitude above the Earth as long as it's going fast enough to not come crashing down to the Earth, or it's not going too fast so that it would drift off into space. And in reality, we have all kinds of satellites at all kinds of orbits orbiting around the Earth at any given moment. They're all going all different kinds of speeds and so on. So what we're going to do today is we're going to figure out how fast it would go depending on what location you would be. So our moon might be, let's suppose it's way out here, so it has an orbit, and all of our different man-made satellites then are at different altitudes as well. So what we're going to look at is how to do these calculations. So first of all, let's think of an object like a satellite, and it's orbiting the Earth. Okay, so what we want to do is ask ourselves what forces are acting on this object. So we have gravity pulling it towards the Earth, and then we have our centrifugal, or our opposite of our centripetal force, pushing it outwards. So in this case then, for it to be in orbit, those two forces have to be balanced, right? If our gravity was too big, our gravity was bigger than our centripetal, then it would come crashing down to the Earth. If our gravity was smaller than our centripetal, and our centripetal was too big, it was going too fast, then it would actually move outwards. And probably what would happen is you'd get sort of a spiral type path, right? If it was going too fast, it would spiral outwards and eventually leave our Earth's orbit altogether. If it was going too slow, it'd probably spiral inwards until it crashed on the Earth. So in terms of our calculations, what we're doing with this is we're just basically using our two forces, and for a satellite to be in orbit, those two forces are going to be equal. So it's similar to what we did before when we were doing roller coaster questions. We just had to balance the two, and we used for force of gravity, we used mass times gravity. But in this case, because we're talking about things orbiting, we would use the big G formula. So G m1 m2 over r squared, and for our centripetal we use mv squared over r. And you can see we have a few things that can cancel out. We have a mass on each side, and that's actually the mass of the satellite. So the only mass that really matters is the mass of the Earth. So the mass of the satellite doesn't really matter, which is kind of interesting. So you think about it, a huge thing like the moon or a little tiny satellite, they actually are not affected any differently. They orbit at the exact same rates. And then we also see we have one radius that's the same for both, so we can cancel those out. So we basically just get G times our mass of the Earth divided by r equals v squared. And that's it. So we can actually use this formula to calculate any sort of a question. So let's try an example. Okay, so let's suppose we have a 30 kilogram satellite, and let's suppose it is 120 kilometers above the Earth. And the question is, find its speed. Okay, so in this case, one thing we got to be careful of, right? We just had in our formula, we got v squared equals gm over r. So our velocity will just be square root of gm over r. So we can plug everything in. Our g is 6.67 to the negative 11 from before. Mass of the Earth, we know, is 5.97 to the 24. And for our radius, we just have to remember to add the radius of the Earth, which was 6.37 to the 6. And now we want to add 120 kilometers, which is 120,000 meters. Add those together, plug that in our formula, and we're done. So in this case, if we actually do this, we'll get a speed of around 7,800. I got 7,833 if we round it off in meters per second. Okay, so what that means is really with this question, the 30 kilogram satellite doesn't matter because it cancels in the formula. So we really only need the distance and the mass of the Earth, and that's it for any kind of question. So we could do the exact same formula again for a question like something going around the moon, for example. So if there's something orbiting the moon, all we need is the mass of the moon and the distance it is away from the center of the moon. Or this would work for the sun or Jupiter or anything else. One other example, I just want to look at a specific type of satellite. We call them either geosynchronous or geostationary. So a geosynchronous orbit is a satellite that looks like it's not moving. So if we picture our Earth, and we know it's rotating around, like it's spinning on its axis. So a geosynchronous satellite is basically rotating at the exact same rate. So it's going at the exact same speed. So if this satellite was, let's suppose it's right over us in Edmonton, if it's geosynchronous, it's always going to be above us. So that means it's rotating at the exact same, or it's orbiting at the exact same rate as our rotation. Therefore, it never moves compared to us, which is important for communication satellites. For example, if you have a satellite TV, you point your satellite dish to the satellite and you get your reception for your different TV channels. If you didn't, if that satellite was moving at a different rate, we'd all constantly be losing signals because it'd be flying at different speeds. So we have a whole bunch of geosynchronous satellites up in orbit, and they're usually used for TV and other communication purposes. So the question is, let's figure out how high the geosynchronous satellite is. What's the radius of that satellite? Okay, so for those kind of questions, we would use our same formula. We have our FC equals to FG, so MV squared over R equals G M1 M2 over R squared. Okay, the problem is though we don't know how fast that satellite's going for it to be geostationary. So we can't solve it for R if we don't know velocity. So what we're going to do is we're going to actually use the other formula for FC, and this is one where we plug in 4 pi R over T for our velocity. So let me just kind of show you that. So we'd have 4 pi R over T, and we're going to square that divided by R. So if we do a whole bunch of rearranging and canceling and so on, it'll actually simplify down to, so our top would be 4 pi squared mass times R over T squared. We'd still get our G M1 M2 over R squared on this side. So we get one of the masses to cancel, and our R will actually move down. So it looks a little bit more complicated, but what we end up getting is 4 pi squared over GM equal to T squared over R cubed. So in this case, we can actually use this formula to figure out what is that height of the satellite. Okay, so we'll use this, I'll rewrite it on the next page, and we'll actually do this calculation. Okay, so if we're looking for, if we're trying to find what is the distance of a geosynchronous satellite, we know everything on this side. We have our 4 pi squared, that's just constant numbers. Our G is 6.67 to the negative 11. And our mass of the Earth is 5.94. Sorry, 5.97 to the 24. And then what we're going to use is our time. So our time, we want to make sure everything's in sort of meters and seconds for this case. So our time, we know we rotate every 24 hours. So we're going to have to change that to seconds. We'll go 24 times 60 times 60. We'll square that, and now we're going to solve it for R cubed. So if we actually plug all that into our calculator and solve it for R cubed and then cube root our answer, we end up actually getting a solution of 4.22 times 10 to the 7 meters. So the only thing we got left to be careful about, remember, that is the distance from the center of the Earth to the center of the satellite. So what we have to do is we have to subtract the radius of the Earth. So if we subtract our 6.37 to the 6, that will be our distance above the surface. So when we do that, we get 3.59 times 10 to the 7 meters. Which, if we actually think about that, that's something close to 36,000, approximately, 359,100, so 35,900 kilometers. So you think about that, that's a massive distance that these geostationary satellites are above our Earth. Okay, so a little bit of a tricky question because you have to use the more complicated formula and then subtract the Earth's radius afterwards to get it. So pretty tough, but it's kind of an interesting question to think about how high up those satellites are. And we're done.